Hello, welcome to Science Visualized. Today we're looking at how NMR spectroscopy works. Now, just as a review, in magnetism, you have what's called magnetic dipoles. In a material that's not magnetized, the dipoles are facing random directions. They're randomly organized. After magnetization, the dipoles become ordered. They all face the same direction. A similar thing works in NMR spectroscopy. In NMR spectroscopy, we're talking about a magnetic nuclear dipoles. So it's focused on proton, that's the nucleus, so proton with a mass of 1, that's hydrogen with a mass of 1, and carbon-13, that's another nuclei. Carbon-12 is not NMR active. Carbon-12, carbon-14, so these are not NMR active. In a sample, we see that the nuclei, remember that's a proton or carbon, if you're looking at carbon or proton NMR, but you could also be looking at other types of NMR where you focus on other types of nuclei. So the nuclei are randomly organized. That means they are facing all directions. But when you introduce a very strong magnetic field facing this direction, see this red arrow? So a very strong magnetic field force, this will force the nuclei to align themselves in such a way that they are parallel. Look at these blue ones. They are parallel to the field. They're facing the same direction with the magnetic force. And a few of them, look at the purple ones. These ones are anti-parallel. Now, while we're still here, consider a situation where the river is flowing this direction. So the current is flowing that direction. The swimmers who are weak or injured will be able to go with the current. So it will be easier for them to swim with the current or float with the current. But only people who are very strong will be able to swim against the current. So that means these people are strong. So the weak ones will swim with the current, same direction. We call that parallel. The strong ones will swim against the current, and therefore we call that anti-parallel. The same principle applies in these nuclei. The nuclei that are facing the same direction with the magnetic field or force have low energy. So these are low energy. Parallel ones have low energy, while anti-parallel ones have high energy. So what happens is that this sample is exposed to another radiation. So you have another radiation coming to the sample, and then it slowly starts to increase the energy of the parallel nuclei, these ones here, increases their energy, until you get to just the right amount of energy where this flips and becomes anti-parallel. So you get just the right amount of energy to cause a flip. That amount of energy required to cause a flip is very sensitive to what we call the chemical environment here. Chemical environment of the nuclei. So that means hydrogens or protons, proton nuclei in different chemical environments will require a different amount of energy to flip. And because of that, we can use the chemical environment, that's the amount of energy required to cause a flip, to get more information about a sample, about that hydrogen that you're looking at. What environment is it in? That proton that carbon that you're looking at, what environment is it in? That energy is measured in chemical shift value, and the unit is ppm, which is parts per million. Parts per million. So you'll see NMR spectrum, the x-axis is always measured in ppm. By the way, the values increase from right to left. So it starts from 0 and then it increases going left. Now the first type of NMR is the proton NMR, where the nuclei that we're looking at is hydrogen with a mass of 1. And proton NMR will start from around 0 ppm all the way to 12 ppm. From around 0 to 1.5 ppm, this region here, you have alkane protons, alkane hydrogens. And then 12 to 14, like that, that's carboxylic acid protons, that hydrogen. Between 9 and 10, you have aldehydes, proton, so that proton. Around 6.8 to 8, that's aromatic protons. So if you have something like benzene, that hydrogen there. Then from 4.5, so around 4.5 to 6.5, this region, that's alkene proton. So if you have an alkene, that hydrogen will be in that region. around 4.5 to 3.5, you have carbon that's connected to oxygen. So if you have a carbon that's connected to oxygen, it could be an alcohol or an ether. If that carbon has a hydrogen, then that will show in around that region. Then after that, we have around 2.5 to 3.5. There you have the carbon that's connected to X. So if that hydrogen is connected to a carbon which is connected to X, that could be a halogen. Remember, that's fluorine, iodine, bromine, and chlorine. Or it could be a nitrogen. It will show up in that region. And then there is another area around, I'll just say around 2.5 ppm. And that's basically for what we call allylic position, allylic protons. And allylic protons are when you have a double bond and then the next carbon. So if that carbon has a hydrogen, that will be the allylic position. This position on the double bond is vinylic position. So this position is vinylic. And then the next carbon becomes the allylic position. So that's proton NMR. It starts from 0 to around 12 ppm. So it increases that with the chemical shift value. We call this area downfield. And then on the right is upfield. So in the downfield area, you have less shielded nuclei. So we call those deshielded. While in the upfield area, you have more shielded, so highly shielded. Okay, next we go to carbon-13 NMR. And it starts from 0 ppm, increasing to the left to about 230 ppm. Between 0 and 20 ppm, you have primary carbons. So those are basically alkanes. That's only a carbon that's connected to only one other carbon. And then around 20 to 30, you have secondary alkanes, secondary carbons. And then from around 25 to 35, you have tertiary alkane. Around 35 to 40, you have quaternary carbon. So an example for quaternary carbon will be if you have something like this. So that carbon there is quaternary because you have 1, 2, 3, 4 alkyl groups connected to it. And then for tertiary, that will be this carbon because you have 1, 2, and 3 alkyl groups connected to it. For secondary, will be this carbon because you have 1 and 2 alkyl groups connected to it. For primary, it will be this carbon because you only have 1 carbon or alkyl group connected to it. Then starting from around 50 to 75, you have carbon that's connected to oxygen. So it could be an alcohol, OH, or an ether. So that carbon will show up at around 50 to 75. So usually for alcohols, around 70 ppm. Next, we have this region here. That's where you have triple bond carbons. Then we have a very big area from around 110 to 155 ppm. That's the alkene carbon. There is a narrower region from around 125, so 125 to 155. So it overlaps with the alkene, and that will be the aromatic carbon. Then the last region is from 155, so around 160, going all the way to 230. That's carbonyl carbon, so carbon connected to double bond oxygen. Thank you very much. If you enjoyed this presentation, please comment on the videos and also subscribe to this channel. I really need your support. Thank you.